Uh, in this talk, I'll briefly talk about some of the advances which we have made in our lab along with all our collaborators globally on some advances of synthetic aperture radar descriptors for land cover characterization. In this brief talk, I'll be specifically talking about agriculture, crops, and urban studies, the descriptors which has been there. So before moving on to them, I'll just briefly talk about, give a very brief background of micro-remote sensing, what synthetic aperture radar data is actually measuring. And from there, moving on to all the descriptors that have been developed and what exactly are they used for. So I'm working in the field of micro-remote sensing, synthetic aperture radar. So as you all know, it's on the scale of centimeter scale wavelength from 0.3 to around 100 centimeter. This is what is used for micro-remote sensing data. Why we use it specifically, of course, for many different reasons, but I'll just give you an example of what it is important for the place where I come from, or from Southeast Asia. This is synthetic aperture radar data, which is a Sentinel-1 data of an area which is in the southern part of India, which is also called the rice bowl of India. These are all rice fields. What you can see is a Sentinel-1 SAR data of PV polarization. And this data is taken or acquired during the southwestern monsoon season. And we can see in this data set of Sentinel-1. The synchronous data set of Sentinel-2 also shows in the false color composite optical image, we see cloud. This is, of course, an hindrance to all applications which could be done for particularly in this season for all remote sensing purpose applications for agriculture, specifically over here in terms of rice. So it is not that's of course optical is not useful, but an optical along with Sentinel, of course, will give you the best possible way to analyze agriculture. So different SAR modalities, of course, we have the dual pore SAR system, which we normally use is the Sentinel-1 dataset, or the upcoming NISAR dataset will be available. What we also call them as wave polarimetry, the way of treating those datasets is also known as the wave polarimetry. The system transmit one polarization and receive in that same or the cross of it. So in terms of Sentinel-1, you have the VV and the VH. And of course, when you move to the full pole scenario, you have it in 4 measurements. So you send 2 polarization X and Y, and you measure the X and the XY, the YY and the YX to have 4 measurements. So these are all measurements which are in complex measurements. These are amplitude and phase measurement. So you have a different representation for dual poles seen and also a different representation, which is a matrix representation for a full pole scene. We have another modality, which is the hybrid modality, where you send a circular one and you measure the linear component. So in this case, you can have RH, RV, or LH energy mode. This is there in the VSAT satellite, which was from India. So the ALOS-2 from Japan and RCM from Canada. These are the different modalities of data sets which are available or will be available in the future. So we have different modalities of data sets. So the idea is that how to extract different information pertaining to different kinds of applications from these kind of data sets. Now, moving ahead with that, there are many kind of techniques which are available to extract information for such kind of data sets. There are different techniques, technologies are available from SAR data. You can do polarimetric SAR data, in short, or SAR, interferometric SAR, the polip SAR, pole SAR, and time SAR. So all these things are available with availability of more and more data sets coming into the picture, and of course with the advent of all the satellites which will be there in the near future. We over here in this center in our group, we work mostly with agriculture on urban, also on biosphere. So what exactly are we measuring? For example, in a SAR sensor, we have electromagnetic waves, planar wave is interacting with the target, and what you're measuring is the scattered wave. So the relationship between the incident and the scattered wave is governed by two complex matrix. It contains the amplitude and the phase information, and the idea is that how well can you extract information out of this complex 2x2 matrix in order to utilize it for various different applications. How do we see these data sets? If we just see the temporal variation of SAR backscattering for agricultural area, this is an area where you have different types of crops, and the color variation shows the temporal variation from May, June, and July over different fields and in different polarization state. This clearly shows that this variability in the scattering type from different crop types gives you a lot of information. The idea is that when this information can be well extracted, then it can lead to many different applications in agriculture. This is the temporal variation. You can also see the dependence on the frequency of different targets. This is again an area from Germany, from Bavaria. This was an airborne campaign which was done in 2000. You can see the variability of different frequency from X band to L band, XC and L, the increasing wavelength, and it is for a particular polarization, which also tells us that the variation of the information, which is dependent on the frequency, is useful. It contains a lot of information which then can be extracted for characterizing data. How are we exactly doing it? We are doing it because of the sensitivity of these targets to this geometry polarization. And this is what exactly has been shown in this schematic diagram, is that when you have the information coming is extracted from an area which is a ground or different kinds of target, you get different kinds of scattering mechanisms. The idea is that how can we characterize these different kinds of scattering mechanisms in order to extract relevant information for different particular cases or different particular applications, be it agriculture, be it urban, ocean, or various other applications which you can think of. The dependence of target geometry and polarization also plays a very important role when we want to characterize soil and vegetation interaction. And these are already done by using physical models from very simple to very complex. The idea is that how do you model such complex natural scenarios. So, but here you measure the information coming from ground or the canopy, the ground canopy, and so on. In a simple way to understand them is how can you see them in terms of a particular polarization by varying the angle of incidence. This is a function of the angle of incidence and of course many other parameters which can be there. So if you can look into that, it's a simple summation of all of them is the total information which you can get, the total basket of information from the target. Now, in the research component of SAR in agriculture, we have many different components, starting from soil moisture to crop risk, and also at the end to have crop mask as an ARD product. So there are various different levels and aspects of user information which can be given for downstream applications. And this is where our expertise lies, this is where we work on. But without going into much of the detail, in this very short presentation, I'll just talk about some of the crop characterization with full polarimetric SAR data. I'll just show a very brief movie of how we can see the radar vegetation index, which is extracted from a full polarimetric SAR data, and you can see the temporal variation of it. On the right side, you have the area, the ground truth mapped with different 5 different crop types, and over there you can on the left hand side you can see the variation of this parameter, which is the generalized radar vegetation index extracted from a full pol data set, gives information about the changes in the structure, the dielectric, and all different physical properties of the crop. And then this could be utilized for further information extraction for analysis for agriculture. I take you to a particular area where we have a lot of work done and a lot of field works have been going on for years. It's in the southern part of India. This is called the rice bowl of India. This image which I showed you before. This is the area where we have different types of crops. There are different kinds of practices, managements, We have the transplanted rice situation over here, and the different scenarios can be seen on different time periods on different phenological stages of transplanted. Another part of this is also the direct seeded rice. The photograph shows the different phenological stages of rice. Now, utilizing this information, when we have the full polarimetric SAR data, how can we assess this? So the top row shows you the false color composite of a full polarimetric SAR data from June to August, where you have the growing stages of rice. And the middle row shows the conventional adult vegetation index, which has been there for a long time. But you can see that unfortunately, this is unable to extract the information or characterize the growth stages of rice, which tells you that even when the crop has already grown, this parameter is unable to detect it or actually reliably tell about the growth stages. Whereas the last row, which is the parameters developed by us, is showing the information content where these stages of rice is correctly characterized on the later stage in July and August. It's much more drastic when we go ahead with the season in the August up to the harvest season. You can still see that in the middle row, it is still unable to characterize those stages, even though the crop is in full maturity stage. It only captures when there is a harvest, because after harvest, there is a roughness in the soil after the crop has been cut. And then it picks up the amount of information which comes from a randomness structure, but this randomness is because of the surface, the crop per se. But whereas this, the generalized vegetation index characterizes very well all the growth stages of rice. And hence, this can be an input to many different models, which utilizes the crop models and for various other applications of in agriculture. For this example, this is only for rice. I move ahead also with crop characterization with dual pore SAR data, which is, as I mentioned earlier, it's like Sentinel-1 type of data. You can do a similar kind of analysis, but then you have to change the way you treat this data. Your model changes. So I'm just showing over here again some images of different timestamp, again from June to July. You can see this is a new index, which is a dual pole vegetation index, which is derived from a Sentinel-1 type data. The previous one, which you have seen, is from the full polarimetric SAR data. Because of the different aspects of the data set, the way you characterize or the way you develop these indices are quite different. Here you can see that this characterizes different stages, and you can see that different crops again. This is the same area, the same field. You can always characterize them very nicely with this kind of this parameter. You can see a comparison of that. A similar comparison of that is also from a full pole and a dual pole seed of the same area. This is the crop map on the right-hand extreme side. You can see that how well it again characterizes. Of course, there's a difference between how you have the information extracted from a full pole and a dual pole, but on a global scale, it still characterizes very well the stages of growth from these two different kinds of crops over here. It can also be used for crop phenology mapping using this advanced descriptor. You can see this is the scene from Sentinel-1 from 12th August. This is another scene from Sentinel-1 from 17th September. You can see that this is the change which is there, and this is because of the change of the type of the phenological stages between an early tillering to a booting stage. So it very well captures this extracted information, and this is all available or all can be done in the snap toolbox. So this allows us also to work on a larger area on different analysis for different kinds of crops and different kinds of area. This new development has also given rise to a kind of a simple way of data-driven segmentation. So all what we have extracted, all this different information from the dual pore seed, can be put into a two-dimensional space in which they can be characterized within this curve, which you can see on that, with the different analysis or different kind of complex, starting from high entropy complex scattering to low entropy pure scattering, which means that at these different stages of the phenological stages, if you extract information, if you extract these two parameters and put them without any further knowledge, they can be segmented on this curve, which then tells you that this is only a data-driven way of segmentation of different phenological stages using these two parameters. And this works well for different kinds of crops and at different phenological stages. This is what all about the crop analysis. I move ahead with this for the built-up analysis. As I mentioned, we talk about two different land cover classes. So this is for a dual pole scene. As we have an index which has been developed for the vegetation, we have also developed an index which is called a dual pole radar vegetation radar built-up index. This characterizes built-up index. So you can see that over 1 year is a 0 to 1 scale. One characterizes all of the urban area. This is an area from Delhi in India. Between it's from Milan, it's from Buenos Aires in Argentina. What you can see is that it goes from red to blue, characterizing urban to areas which are non-urban. So this is a continuous at a scale of continuous from 0 to 1, and it well characterizes this dual pole built-up index. You can just make a threshold depending upon the physical constraints, and that physical constraint is taken from the data. And if you just make a very simple threshold for built-up and non-built-up, you can see that we are very well able to characterize the built-up area from any other kind of a structure. It captures very well small settlements and small villages and everything. And all of them has been proved with a ground truth available for all these data sets. Moving ahead from there, you can also have something which characterizes surface indexes, which is there are surface indexes. Here, 1 is blue, just the opposite, and 0 is over here red. You can see that all this, the area in the first image at the bottom of it is capturing all the fields which are bare area, and over on the top it is characterized as water area. So all these are again well characterized or captured by the surface indices. So utilizing those two parameters, we moved ahead to give some further information and higher order information, which are scattering power components. And these are very useful in the field of SAR, mostly in the field of polarimetric SAR data analysis, is that with these three components of power, which can be a crude way of analyzing or classifying different kinds of target in a scene. So you have the red to be as kind of a double bounce and an even bounce kind of scattering coming from mostly urban areas, built-up structure. And the middle one is something like green, which is kind of coming from a randomness, mostly kind of a residual kind of scattering, but mostly coming from vegetation, forest, and so on, random. And the surface one coming from mostly flat area, which is water body, flat surfaces, small water bodies over here, you can see. What all we can see is these areas which shows the cropland area, lake area, and so on, they are well captured with this power. And then the idea is that this power could be then further utilized for different application in classification, segmentation, and so on. Moving ahead, this is another area from the area of Buenos Aires. You can see so this also shows very well the areas under with these powers. But then when we have all this information, the easiest way or the best way to put them in a cloud-based clustering framework, because these data sets are large, this can be utilized for large area analysis, and the best way of doing it is to utilize the Google Earth Engine. And this has been done over here, that we take these parameters, put it into Google Earth Engine, and we do a simple k-means clustering, because that's the simple and the easiest and the faster way of doing it. You can put them, and we can see that we can very well classify them. And these are the dominant. You can see on the right hand side is a Sentinel-2 force color composite with some dominant land covers, and these are also can be seen with these parameters which are just shown extracted and put them, and we can see that all these areas can be well clustered. This is again Buenos Aires. Over here you can see that we are able to very well cluster or make the classification of the urban, the water body, the area which is tree covered, forest, and so on. So the idea is that before concluding, the idea is that utilization of all these parameters is useful for the present and of course the upcoming all these SAR missions which are coming up. Some of them are already there, some of them are coming up. And it's an exciting phase in which all these parameters could be utilized. And of course, these can be well utilized in a cloud-based platform. You can utilize all of them. And this will be utilized, and we can see some examples of that, that it can be very well utilized for different areas, large area, for huge amount of data. And this will give you all this information which can be used for characterizing crops and urban areas and any other different kind of land cover types which you would like to do your field of research is. All this functionality which we have shown, especially for the agriculture, are all available in Snap. You can utilize them. These are all available. The publications along with that are also available. And this will be useful for all of you, which you can utilize Sentinel-1 data set and can extract all this information, everything available in Snap. And everything is also available for agriculture in this book, which has been composed by us. It characterizes from basic SAR polarimetry to advanced vegetation indices and all biophysical retrieval parameters. I believe we all in my lab, and we all believe in the replicability and reproducibility of research. So all what I have shown is available on GitHub and Snap and as a plugin to QGIS. If you need any more information, I'll be happy to share more information and all the tools which have been shown over here. Finally, thanks to the collaborator with whom I have been working for very long, and this is all has been possible with their support. Thank you very much.